welcome. My name is Denzil Ribeiro. I'm a product manager in the Hyperscale team. This session is going to be about building applications on Hyperscale. And so we'll go over a few tenets of Hyperscale. We'll look at the overview, the use cases, architecture, hopefully a bunch of demos. We'll look at serverless that was recently announced and how that works on Hyperscale, and some of the other roadmap or recently released features. So from a Hyperscale perspective, what is Hyperscale? It's really a cloud-native relational database architecture exposed as a tier in SQL Database. So it's the same SQL Server engine that we know and love, except that it has some key tenets in terms of separation of storage of compute, solves some VLDB or large database problems because it scales up to 100 terabytes. It has a resilient architecture and really is designed for the cloud. So the first thing I want you to take from this is, it's not new SQL, if you will. So it has a time-tested database engine. It has multi-modal support with graph, column store, row store, all within the same table. It has features like optimized locking that were talked about in today's keynote. It has leading performance. Then also it has a lot of the intelligent database features that we see on the on-premise with IQP, param sniffing, all the memory grant and feedback systems that exist. The HA and business continuity with Azure SQL that you get, leading SLAs of 4 nines. You get zone redundancy, ability to set up geo-replication and geo-failover within a click of a button. And things like long-term retention. Then security-wise, we have a ton of features applicable throughout the SQL tiers. And then we have investments, like you saw in the keynote demo, around rich app dev, local emulators, easy deployments, Azure functions, so on and so forth. So all those things that come with the other tiers also come with Hyperscale. Often, the question is Hyperscale something different than the rest of SQL? And the answer is no, other than the scalability aspects of it. Another big question I get is Hyperscale only when your database grows large? And that's not how we look at it. Separation of storage and compute enables various scenarios. You can always start small. We have auto-scaling storage, so we start with a 10 gig database, and as you need, the 10 gig grows to 20 gigs, and so on and so forth. So we have auto-scaling storage that grows as you use it. Then you have compute choices being provisioned, which allows you to scale from 2 to 128 vCores. Provision scaling is pretty fast. So in a minute, you've scaled up, and downtime is in the 10-second time frame. So retry logic in your app, you won't even realize a disconnect. And then we'll talk more about serverless in a second. But you have also the serverless auto-scaling, which is in preview now, which enables almost instantaneous scale-up and scale-down of CPU, memory, and some of the caches. We'll look at that in much more detail. As the app grows bigger, you might have needs around HA and resiliency. So you're enabled to add a high availability replica for HA that enables the hot failover aspect, and can scale up as we talked about. We also introduce memory optimized objectives. We'll talk about some of the tiers there. And then if you need cross-region business continuity, you have GeoDR to replicate to cross regions. As the app needs to scale out, as you can see, we have read scales, for example, an app that serves near real-time analytics, or an app which serves API calls, which needs read scale out. Besides the HA replicas, you have this concept of named replicas, which allows you to scale out reads across the ecosystem, right? So the same data you're writing once, shared storage, scale out reads across 30 replicas. So you can have up to 30 replicas, and then you can scale out cross-region with geo replicas as well. So what are some of the workload patterns, from a Hyperscale perspective? We see a lot of, customers building cloud-born applications, who are trying to future-proof their applications. You have workload patterns that require independent scaling of compute and storage. Compute scaling is a big one. You have workload patterns that require independent read and write scaling. APIs is a very common pattern. You have near real-time analytics where you have, say, an IoT app or some data coming in from a system where you want near real-time analytics, which you can do with read scale out. And then last but not the least, we have a bunch of ISVs modernizing to SaaS. And then you have the core data marts and SMP data warehouse scenarios on hyperscale. Right? So that's that. So let's look at more of the hyperscale architecture under the hood and how this works. The first thing we see is a separation of compute and storage. Your connection point as an application is always to compute. Compute has its own local memory and this blue box, which is the resilient cache. And it's a smart SSD cache. So whatever doesn't fit in memory as we access and we have hot pages, we actually cache in that cache so that you don't go remote off node for any of the storage requirements for pages that are hot. In addition to that, all your DML changes or data changes go in this red line to something called a log service. The log service is where all your writes go. Writes never go directly to the storage. And the log service then pushes this writes out to this layer called page servers. These are your storage layer. This is not accessible to the application, right? Under this boundary, it's really Microsoft managed. Over this boundary is what you have control over and connect and see, right? So what this log service does is it distributes this log or these inserts, updates, deletes, and all the data changes to the page servers or set of page servers. Page servers is a storage layer, which you can think of each page server or each chunk as a partition of your database, right? It's a chunk of your database. Say, let's say 128 gigs chunk of your database. So if you have 1 terabyte, you have 8 of these, if you will. And each of them are resilient in nature. They have a replica, right? So they're independent. Replica is independent on of each other. And so they apply log these changes that come for durability purposes, right? And they're a covering cache. So they hold all that data in local SSD. And last but not the least, you have the durable storage. So these could go down, or we could reprovision, and durable storage is still in Azure Standard Storage. That's the last block. You don't directly interact from compute to this durable storage. This is only needed when these page servers come up and see this data. Similarly, like the data, you have log as well, which is archived to durable storage via D-stage process. And that's depending on your retention period. Default is 7 days. You can configure retention up to 35 days. Log is maintained for that long in the short-term retention phase. Then you can have, for availability reasons, you can have 0 to 4 replicas. These replicas are failover targets. So if this compute fails for whatever reason, the secondary becomes a primary. And you're also enabled to route read workload with app intent equal to read only to this set of replicas. And it gets load balanced across them. Right? So that's one more thing. And last but not the least, we have this set of named replicas. And so log is applied again from the log service to these replicas. And only the log is applied of the pages that they're actually accessing. So if you make a change and that page is never accessed here, the log is applied only to the page servers. Only partial log is applied depending on what is needed by the read workload. The named replicas give you a different isolation because they can be separated, allow workload isolation can exist on a different server, so on and so forth. And we'll see some details around that in a bit. Now, what is that log service? We talked about the log service block, but what is that log service under the hood? This serves log to all components in the system. And we have a commit transaction, which is your unit of work when you're doing any DML. Compute writes a commit transaction. You can think of this log service as an availability group on SQL Server with a primary and 2 secondaries that only has an LDF file. So the only job is log hardening. It doesn't do log apply. It doesn't have data files, anything of that sort. So when you commit a transaction, effectively, you're writing to this log service. You write to the primary replica, and it quorum commits with one of the secondaries, right? And then this log service then distributes log to all the other components in the system. These can be page servers. This can be also any of the compute readable secondaries which are there for read scale. Right? So think of this as a stripped-down SQL Server only servicing that log hardening portion. It's not like the full SQL Server executable. And then, of course, I mean, you have your normal wait types. So, you know, if you're waiting on a write to the log, the normal wait type is write log, just like it is on an on-premise or any other SQL tier. The next layer is, the page server. Page server, like we talked about, is a building block of that auto-scaling storage architecture. Each page server has a replica, and it hosts a chunk of the database. It also runs SQL Server.exe. It has a covering SSD cache, so it has all the data you need for that chunk of the database, right? And when you're doing a read from compute, you know which page server to go to. At the back end of this, you actually have a bunch of blobs. So even if this is a 128 gig chunk, this is chunked for durable storage into multiple blobs, right? And the log service then log applies any change that compute makes to keep this chunk up to date with the latest DML that you're doing. So that's page server. So a couple of things in that. Page server also does a bunch of other work. It does things like checkpoints. It readies snapshots from backups from snapshots. All our backups, even in 100 terabytes database, are taken with snapshots, so they're almost instantaneous. Restores of database, if it's 1 terabyte or 10 terabytes, are constant time because we restore from snapshots. So, even if for a 50 terabyte restore, it should be in the 20-25 minutes, 20-minute range, 0 to 20-minute range, somewhere there. So this also has a other side effect of offloading some of that work from compute, saving precious CPU cycles for your workload on compute. Right? And then we changed an architecture a little bit. So of this storage component, we had a 1:1 mapping between a page server and what you saw as a file. So if you have an MDF or LDF, we would have one page server per file. And this is actually to facilitate upgrades. We've changed that architecture actually where what you see as one file on compute can be split up to allow further elasticity. And also to be able to break down these blobs into small chunks to enable, a bunch of scenarios around, unexpected failures, resiliency, isolation from Azure storage. Even if the storage goes down, now we have ability to queue all the writes and not impact the database with these changes in architecture. Last but not least, it's last slide in kind of the architecture aspect, and this is important to know how reads are done, right? So we have this durable storage. If page servers, if all of them went down, or if you were restoring a database, you don't have this compute provision. All you have is the durable storage, right? So we first provision them, we create snapshots, we provision them, and we seed these from the blob. Once that is done, always page server is up, and your access really from compute never goes to the blob. If you issue a read, first you'll try to access the page in main memory. If the page is not in main memory, it'll go to this cache, which is a smart cache, which caches hot pages locally. The cache here is 3 times the amount of memory. So if you have 5 gigs per core, you have 15 gigs of this local SSD cache. So you're thinking 1 millisecond I/O times because it's a local cache which has all your hot pages. If the data is not in the RBPX cache, then we issue a get page to the appropriate page server. We know what file ID we are reading from, what page we're reading from. And so we issue a get page to this page server. If this page is not caught up, then it goes to the log service, gets the remainder of the log, applies it, and returns the page. If this page is caught up, it just returns the page. And we're talking in the 2 millisecond range at the high P90s is the latency from compute to actually remote page server. Third thing we'll talk about is named replicas. I briefly mentioned named replicas. Named replicas are scale units for reads. There are some distinct things about named replicas. One thing is they can exist on they can be, first of all, the different size as primary. So if you have a primary of 16 vCore, you can have a named replica of 2 vCore, or you can have a named replica of 80 vCore, right? So the size can be different. And that really depends on your read workload that you're servicing. That's one thing. The second thing is they can be hosted on a different logical server. And why is that important? That's important for workload isolation. So you could have a different security. Say you have another team that read access to this data. You can have different security and a dedicated endpoint to this named replica that doesn't interfere with your primary at all. All right, so this could be server 1, this could be server 2, endpoint with its own login security, so on and so forth. But still, this log service still applies all the changes to this named replica. And you still have only one copy of storage. You don't have duplication of storage if you create multiple of these named replicas. Now, you can do read scale with HA replicas too. You can have 0 to 4. But you don't get the isolation in terms of these have to be the same size as the main replica because they are also failover targets. So if this goes down, it fails over only to the HA replicas. It won't fail over to this set of named replicas. These are purely used for read scale, right? The limitation in named replicas, it has to be in the same region because storage is one copy of storage. For anything off region, you'll need to use geo-replication. Right? So I think I covered. And you can have up to 30 of these here. So it's simple to create a named replica. I'm not going to go through the creation, but it's alter database, add secondary server on T-SQL. You have the CLI and API constructs as well as portal to create a named replica. It's just a replica type. Every time you create a replica type, you'll get a choice of is this a geo replica or named replica. And choosing named replica effectively gives you just this compute endpoint sharing the storage to read scale. Then we have GeoDR, which is used more for regional failover. So in GeoDR, so let's talk first about GeoDR and then failover groups. GeoDR is async replication, which is across region. Right? You can have RAID scale components, and everything that we talked in the previous slide on named replicas or that topology is also available on GeoDR. So you can have like all this section on the geo side as well. For simplicity, I'm not showing that in this diagram. So each region has its own copy of data because, of course, a storage account doesn't span regions, so we replicate data. So you're paying for data twice in GeoDR, but it gives you regional resiliency, right? And it's asynchronous in nature, but it allows you to have a planned or unplanned failover. What that means is failover or failover allow data loss if you're thinking of always-on availability groups, right? So failover will catch up that tail of the log before it does failover. And failover allow data loss you'll use if you, for example, lose a region totally and you need to failover your app stack to another region and it's important for you to be up rather than data. Then you have a concept of failover groups. Failover groups is a manageability construct which is kind of like your availability group listeners, right? So you can group a set of databases in a failover group and fail them as a unit. And what this gives you is two things. A, it allows you to manage a group of databases. B, it gives you two endpoints which are dedicated. So you have a read-write listener and a read-only listener. And when you fail a failover group to the other region, your app doesn't change any connection strings. So your read-write listener will remain the same, and DNS aliases are changed and so on and so forth. So your app talking to it will still be routed to the read-write replica, whichever region that is. And then similarly, your read-only one will go to the read-only region, if you will. But this is for cross-region DR. Of course, storage copy is there. Then last but not the least, from a business continuity perspective, we have zone resiliency. So each Azure region comprises of multiple zones. And if you want within region resiliency, multi-AZ is the way to go, or zone resiliency. you can configure a database to have multi-AZ. What we do is we spread those components across multiple zones. So if a zone particularly goes down, you still have the replicas on another zone for the database to keep functioning. So this is not for the full region down scenario. It's a zone within a region having a problem, right? So for that, we need a primary and an HA replica. So multi-AZ is there on Hyperscale only with the addition of an HA replica. You can't have just a single replica compute. And we spread out the log service like you see in the diagram across the multiple zones since it has 3 nodes. And page servers have 2 replicas each. They're spread out across the zones. So if one zone goes down, you still have full access to the database. Even if one of the computes go down, you have access to the primary, and we'll create a compute in the remainder of the zones, right? So it's zone resilient in that way. Now let's go take a look at a demo and how this looks like. So we have a database here, compute and storage, and we have a couple replicas here. So this is the replica topology. So you see in these replicas, there'll be one primary, which is in West US, and that primary is configured to have a HA replica, which you see one there. Then you have the geo replica, which is in the paired region, right, Western Central US, and then you have a named replica. So these are the 3 types of replicas I've used right now in my demo. And what we'll see is we'll direct workload to each of these and see how they behave. So here I have 2 groups in this application. One is a read-write group and a read-only group. The read-only group is going to direct workload only at the name replica. I'm going to launch it. It has 160 threads, and it's going to direct some workload to that read replica. Right? So only thing we're doing is reads at this point. We have not introduced the write workload. So reads are going on, and we'll look at some of the perf throughput, if you will. I will zoom in, and we can see we are throughputing about 26,000 transactions per second, or 26,000 batch requests per second on the read workload. And this is a dashboard based on Grafana. We'll see CPU is at about 46%, right? And if the right side of it is batch requests. Let's refresh and give it a second. We'll look at batch requests, and we are at 26,000 batch requests per second, which is your requests coming into SQL Server. So we're going to stop this, and now I'm going to introduce the read-write workload on the primary to show you that the read-write workload doesn't really affect the read-only workload. So we have 40 threads of read-write workload going to the primary, and the rest going to the named replica. Before that, I'm going to show some DMVs. We introduced the sys.dm database replica states to include Hyperscale, which gives you replicas across the topology. So you have the primary. It shows you it's local and it's primary. That's the primary replica. And then you have the other replicas. And if you run the same thing on a replica, it'll tell you which replica is local, right? So it gives you the replica ID. It also gives you a few other things like when is the last LSN sent to the replica, so on and so forth. And then you have the geo-replica link status, DMV, which gives you the lag between the regions. You'll see that replication lag seconds where my pointer is, and you see it's between 0 and 1 second, this asynchronous replication to the other region. Right? So we'll go back now that the workload has stabilized, and we'll see that introduction of the read-write workload has done nothing in terms of the read workload. Read workload is still maintaining what it was before introduction of read-write. So scalability is kind of maintained, though you have read-write workload introduced. If you see, this is still 26.7 thousand batch requests per second. And if we flip over on the primary, we've actually introduced 15,000 batch requests per second of read-write workload in addition to the read workload. So your system is cumulatively getting 45,000 batch requests per second. Right? So you can see side by side, like both of them are running, and you have workload going to both of the replicas, both primary and read-write. The primary also I want to show you because it's named Replica. The primary is running 16 vCores. The secondary is running 24 vCores. You could argue, okay, I have my 60% CPU. I could probably lower this and save some time on this. But that's showing you kind of the aspect of scalability with named replicas as you see, that's a read-only workload. That's even a different, that resides on the same server name, but it could be a different server name, right? So we'll stop this. And then last but not the least, let's do a quick geo failover. If we see this server is Denzil Central West US, which is a replica, and I'm going to do a failover. And the construct failover here is important because this is failover where it'll do a catch-up and then failover. So this is a planned failover. This is not a data loss failover. So it's async replication. It has to actually catch up, and then it'll failover to the other region. Now, in case of a region being down, if you wanted to get it up, failover allow data loss is what you would use as the construct to failover, right? So that's more of a forced failover than a planned failover. And you can see, I mean, it took 30 seconds even for a planned failover to failover across region. And now if you had a failover group defined, then your application would talk to the read-write listener, would be redirected to the other region. So that's that in a nutshell. Next, let's look at serverless and what serverless gives us. So this next slide is really not hyperscale specific. These are tenets of serverless. Serverless exists on general purpose today on Azure SQL, and we've introduced it in preview in Hyperscale. So there are two tenets of serverless. One is autoscale and one is auto-pause resume. Right? So autoscale allows you to float between the min and max vCores and memory. And auto-pause delay allows you to actually deactivate a database. And that's there on general purpose, not yet there on Hyperscale, right? So that's one. So, but it's done for price optimizations. As you can see in the graph here, the auto-scaling, you can peak from something low to max CPU usage. The ratio, as you can see, is 8x of min to max. So if you go 2 to 16 is fine, 1 to 8 is fine. You can't go 2 to 80 today. So it's a 8x ratio of min to max. And then you build according to kind of the usage. And then in pause resume on general purpose, when it's paused, you're only paying for storage. You don't pay for any compute, right? Then this billing is based on compute used per second. It's a per second billing, so it's really granular from that perspective. It's billing for CPU. We think of CPU for sure, but we don't think of memory, but it's CPU and memory. It's not only CPU in this case. Right? And the usage pattern is, of course, if you're always pegged at the max, or if you're pegged at more than 50% of the max, this will prove out to be more expensive because there is a price premium over provisioned for serverless, right? So you have workloads that are intermittent, unpredictable usage. Your average utilization is below kind of the 50% mark, if you will. Right? So, and then it's all the management benefits exist. So here's how we look at difference kind of between serverless and compute. You can independently scale CPU and memory. So if you need more memory, memory can burst, whereas CPU is low. Or if you need more CPU, memory can burst though you're lower in CPU, or you can need more CPU when there's a low memory profile. So both bursting is allowed. If you think of provisioned, we get 5 gigs per core. So as you kind of scale up, cores, you get proportional memory. So the scale is kind of linear from that perspective. So that's kind of the difference, right? And the scale-up latency, I often get questions. It is almost instantaneously in the high percentiles, and there's no connection. Drop. So in the P90s and up, there's no connection drop at all. Right? Now, there can be cases where you need to move you off to another node where there'll be a connection drop, but the downtime then is like a compute scale-up of provision. In provision case, every time you scale up from one to another, the SQL engine restarts, so your connections are dropped. right? Of course, retry logic is recommended in both places, but most of these times you don't like even notice it because it's instantaneously. You're within the node. There's no restart, no impact to the app at all. And then let's talk about what you get in hyperscale and serverless. You get kind of the benefits of both in one. So you have automatic compute scaling up to 80 cores. You have auto-scaling independently on primary HA replica and named replica. So if you have an HA replica, which is not doing read scale work, or a named replica, which is not doing work, it's not like because primary is being used, you're being billed there. So it's on a per replica, whatever workload is coming to that replica basis, right? Then, auto-scaling, we talked about CPU and memory. Of course, it's hyperscale is a higher performance tier than GP, so you get better performance, automatic storage management, all the benefits of hyperscale with the benefits of serverless auto-scale without you having to manage the provision auto-scale, right? So let's look at kind of a demo now of what hyperscale serverless looks like. You saw a little bit of that in the keynote, but we'll look at it in a little more detail. Right, so we have the hyperscale tier there, and your choices are provisioned or serverless. Right, serverless is per second based on vCores used. Provisioned is pre-allocated, of course, bill per hour. That's a big difference. You see the rates there. The replica is a little cheaper than primary. That's per vCore second on the right. And then you see the configuration there of min and max vCores. In this case, it's 2:16, but it's an 8x factor of min and max that you have to maintain. Right? So that's kind of, and it'll automatically scale between that min and max. And then so next we'll look at kind of the replicas aspect of it, that you can configure each of those replicas differently. You can have a mix and match of serverless and provision. You're not limited to one type or the other. So a replica could be serverless, the primary could be provisioned, or the other way around. In this case, I have actually both of them, the primary and a named replica as serverless, because I wanted to show performance difference is really negligible. So and we'll start a workload now to see kind of some of the scaling aspects. So I started a workload for serverless. It has started right now, and we'll go and look at kind of the metrics. So we see batch requests is the top metric. You see the slow, it's HS_S, indicates serverless. The max is 16 vCores. The max memory is 48 gigs. The max memory, by the way, ratio is a little less than provision. Batch requests here are 24,000 batch requests per second. It's climbed up quickly. An average CPU that you see, this is the same as DMDB resource stats, is a percentage of the max. It's not a percentage of, it's not kind of what's currently used, it's a percentage of max. As the batch requests go up, you see your resource usage go up, both in CPU as well as in memory. Right? We can refresh the dashboard. And we'll look at some other counters. You'll see billing is a little behind. Billing is usually one or 2 minutes behind in metrics. But we'll look at some of the perf_mon counters that we are familiar with. Total server memory being one. Total server memory is what we are currently at. And you see it growing. And target is what we can actually grow to. So we grew from like 9.5 gigs to 40 gigs in no time because we needed it. And memory is a part of the billing. And most of that consumption really comes from buffer pool, which is caching your data pages, right? So we saw kind of that aspect of it. If we zoom out to the last 3 hours, in this demo, you'll see peaks and valleys. The top chart showing workload, right? Workloads has bursted up, and is really high throughput at like 23,000 batches, and then really it's almost 0 batch requests per second. It's idle. It's an intermittent pattern. You'll see 2 charts on this middle thing. The one thing I want to point out is memory. Memory reclamation is a little slower. CPU is almost instantaneous. And we don't really reclaim memory super quick because other workload that comes in otherwise would hit the performance penalty of remote access. But you'll see resource usage and app CPU build is your metric to see the billing unit. Right? So as resource usage tamps down, your CPU usage go down, memory reclaim is a little slower. Last but not the least, if you look at the 12-hour chunk, when we are not using anything, you only build the minimum vCore per billing. So minimum vCore, minimum memory is a thing, so you're built for that. One more thing I wanted to show you on the dashboard is, here is resource usage. We've seen this. This is the same metrics that we have. You can add charts for, there are two things, app CPU build and app CPU HA build. App CPU build HA replicas, right? So those give you the billing across kind of the HA replicas and the primary. And you can see the orange line is almost 0 because we are really not doing rescale on the HA replica. We're just putting workload on the primary compute. So billing is independent on replicas based on what workload those have. And these correspond to kind of really the workload on the replica. Right, so that's in a nutshell. Few other things from a preview perspective. We have this thing called Hyperscale Premium Series. It's a Hyperscale-only service objective. So these are new generation CPUs, and it's faster than Gen 5. Gen 5 is a public offer that we have for all the tiers. We've introduced these Hyperscale Premium Series, just for Hyperscale. So there are two kind of, buckets of these. One is Premium Series with scale up to 128 vCores. Gen 5 scaled up only to 80 vCores. Premium Series goes up to 128 vCores. This is very similar to Gen 5 in that the memory to core ratio is really the same. It's the same price point, but it's a faster generation of CPUs. So you will see a perf boost, and I'll show you a demo in a second. The other aspect of it is Premium Series memory optimized. This does have a price premium of 40%, but you get double the memory per core. So it's 10.2 gigs per vCore of memory. So this is great for kind of analytic workloads, things with column stores, which are more memory hungry than maybe just a seek type workload. So this goes up to 80 vCores. It's great for analytics, like I said, or hybrid workloads. Some of the early preview limitations, and actually I might have to update. We released a couple more regions. Maybe it's in 14 regions now. So we have some early preview limitations. The main one right now is maintenance windows, which we'll plan to support. And then we are rolling it out really across the rest of the regions. It's just a capacity thing. We're rolling out capacity. We expect this over the next 3 months to have it in all regions. Right? So what you'll see on the portal is really Premium Series or Premium Series memory optimized. And then Gen 5, which is existing, is called Standard Series now. Gen 4 is, for all practical purposes, deprecated. So you shouldn't see this choice anymore. It's deprecated. I think 31st March is the last day you can have a Gen 4. So let's look at kind of like a demo of what this perf looks like. So this is HammerDB. You've seen HammerDB before. So it's running a TPCC workload. Right? As we look at transaction per second, I start the workload. I'm doing this on a 32 vCore Gen 5 machine. You'll see that we are at around 370 odd TPM. It'll flutter somewhere between 360 and 380 transactions per minute on Gen 5. Right? We'll see the service objective is HS_Gen5_32. Couple things DMVs folks are not very familiar with. One I love is DM Resource Governor Workload History Groups EX. I know it's a mouthful, but it has a bunch of statistics for each workload group. So you have reads, writes, CPU, a bunch of other details, right? And it captures like last 40 minutes of data. And you see not only the user workload group, you also see the internal workload groups. Here I'm filtering on user primary group, and I'm looking at delta CPU millisecond usage, right? So the interval is 20 seconds. Duration MS is the interval. And you can see we are using, at any interval, 16 to 17 seconds of CPU per interval, which is 80% CPU. Other thing I wanted to show you is in this DMV, we collect even the internal workload groups. So you can see CPU across even internal components, right? Across all workload groups, user plus internal, you see that the usage of CPU is almost 22 out of the 32 vCores. 22 seconds out of every 32 elapsed seconds. So that's 383,000 TPM. So if we, so you see batch requests also another thing we'll compare is 6.33 batch requests per second, 6.3K batch requests per second. Let's flip and do, the premium series now. Premium series 128V core. This is not memory optimized. And we'll scale up, to the same 32V cores and restart the HammerDB. The scale up is generally quick. I've time-lapsed this a little bit to save some time. And if we start HammerDB, we should see a significant perf bump, right? The slow or the service objective that you'll see is HS PRMS 32. So if we do a select star from database service objectives internally, we'll see the HS underscore PRMS premium series underscore 32. And then, if we look at kind of like batch requests per second, they've gone up quite a bit. They'll still go up further, but it was 6.3 thousand odd. Our TPM has gone up to 536,000 from the 383 odd thousand. CPU is still the same. Like I said, it's newer generation hardware, better frequency CPUs. From that perspective, so percent CPU is still remaining kind of the same, so you have more headroom. But your throughput and your latency of your workload has improved from that perspective, right? So that's kind of, in a nutshell, premium series. So the other option in premium series is this memory optimized. So memory optimized series now, what I've done is to demonstrate this is to show you the difference between non-memory optimized premium and memory optimized premium. Right, so we have one primary and one read-only replica, and really I'm just going to do read workload. There's no read-write here. I'm just using primary as one of the things. And one of them is premium series ATV core. The other one is memory optimized ATV core. And we're going to run a query on a really large table, and see how that kind of pans out. So if you look at this line item and supplier table, it has quite a few rows. I can't even count. I think it's 600 billion rows. Pretty large table, 10 terabyte TPCH, right? And order table has a little less. So I'm going to run this query. Service objectives, you'll see in this has this MOPRMS. MOPRMS is memory optimized premium series. So that's how you distinguish that. And then we'll run kind of the query, which does an aggregate. And just to show you that both of the tables actually have the same, you can see the number of rows are the same. They're named replica, no tricks. And the other one will show you PRMS 80. So both are 80 vCores, the only difference being the memory in between these two. Right? So if you look at memory, one has 387 gigs per core, total, sorry. The other one has 802 gigs of memory, right? So it's significantly more. It's double the memory, from that perspective. So let's run this query. It's a query which does a sum and aggregate. I'm going to run it on both, slows, if you will, and you'll see kind of this does a sum of quantity, etc. Count big. From the line item table, and it's with a predicate and a group by column, right? So we get the results pretty quick. It's a standard analytic type query. You have a predicate, and if we look at the time frame, it ran in 12 seconds on the memory optimized slow. So that's 12 seconds here. And just to show you the cardinality of the table and what we've kind of like touched here. We see the cardinality of the table is what we have seen before, all right? It's a huge table. And then the fact that, we have a predicate ship date between, and it's a partition table, but we're still touching kind of all the 262 partitions. We see kind of actual partition count as 262, and actual partitions accessed is 1 to 262, right? So, and each thread really, if we zoom in, is doing a scan of all that data, right? So you'll see we have gone 80 ways because of DOP. We have maxed up 0 here, and you have a bunch of threads reading a ton of data. So looking at kind of the non-memory optimized slow, that also finished, but it took 22 seconds. So you see a huge improvement in the column store type stuff with memory optimized, right? Yeah. Last but not the least, we have a couple public preview features which have been blockers in the past, which should go GA relatively soon. One is short-term retention greater than 7 days. We allow up to 35 days of short-term retention. It's in public preview. We expect to GA it, probably this half of the year. And the other one is long-term backup retention, which wasn't there. We've introduced it not long ago. That enables up to 10 years backup retention, and you can configure a policy to state kind of what's your backup types and you need it at what frequency. Right, so last but not least, we have a bunch of customer stories. I'll upload the deck. Would love to take questions if they are at this point. I don't know if there are online questions at all. If not, if there are any questions, happy to take questions, answer any questions one-on-one. If you have experience with Hyperscale, would love to know your experience and where we fall short or where we can improve as a service. No? Yep. Go ahead.
How do you know, or how does it determine what to get out of memory? How does it choose what gets taken out?
OK, so the question is, how does SQL Server determine how much memory it uses? Did I get it?
Yeah, when it scales down.
OK, when it scales down, so we have a reclamation policy that what is not in used, it uses LRU type semantics, least recently used type semantics to scale down caches. And we scale down two things. We scale down main memory. We also scale down the resilient buffer pool extension, which is that local cache. Because we're giving you the price benefit of not charging for memory. But it scales down in steps, as you can see. We are not super aggressive about scaling down memory, because if you were and a query comes in, then you're doing remote reads to populate memory, right? But it's based on least recently used type pages. So your hotter pages will remain longer than maybe your less hot pages in memory. Sure?
So one of the features that was announced for 22 is query store on readable secondary.
Yes. I can't commit to dates, but yes, we are looking at that, working on that. So. Yes, we intend Hyperscale to be feature parity. We have had some gaps in the past. We believe they're all closed down now. There's significant investment in this as the future. Yeah.
I've actually got a ton more questions.
Sure. I think we have 2 more minutes, so we can take another one. Yep.
Do you have experience what happens if you use Azure Data Factory to copy data into it and scaling occurs while the copy goes on?
Yes.
We try logic in LLDP applications. I think we understand.
Yeah.
How does it work with batches?
So yeah, that's always a bit of a challenge, right? So large transactions. I mean, if they're small transactions, sure. Your data pipeline application still, if you manually scale up, in serverless, it should not affect in most times because, I mean, it's just auto-scaling without a restart of the engine, right? So there is no impact in serverless unless you're moved off node, which is a rarity. Now, in provisioned, you will have the 10-second blip, right? So in a data load scenario, you have to maintain sizable transactions and read-write. If you maintain a 2-hour transaction, you're going to roll back. You're going to have to redo all the 2 hours of work, right? So from a pipeline restartability perspective, yes, you have to think of, and that's true of the cloud in general, not just Hyperscale. You don't want these large chunks of work which are all or nothing, if possible, right? OK, thank you, folks. I appreciate the time.